Okay, is the screen visible to you?
Yes, sir.
Yes, sir, it is.
Okay. Okay. In the post mid-semester part, we will quickly wind up the remaining parts of C and a little bit on data structures, if time permits. I think we have just a couple of, or I would say, four weeks or so in order to complete the syllabus. And definitely we cannot do it as we do in a normal semester. Anyway, still it is our duty to get you introduced to most important topics that remain in this course. Okay, so I will start with three, I would say in a sense, three more advanced data types. So today I will talk about uh, two-dimensional arrays. And things called structures. And if time permits, I will just introduce to you what is meant by pointers. Okay. So these are more, I would say, advanced data types or data structures than whatever you have seen so far, like integers, uh, characters, floating point numbers, even one-dimensional arrays. Maybe I start with these two-dimensional arrays. So one-dimensional array is something like this. Recall. Okay, so it's an array A of certain data types, and the individual locations are accessed as 0, 1 to A0, A1, A2 up to some size -1. Where S is the allocation size. So for example, we can have an array A of size 10 like this. Okay. Now, if I now want to generalize this concept to a two-dimensional array, in fact, there is no harm in talk about three-dimensional, four-dimensional arrays, but for practical purposes, two-dimensional arrays are more, I would say, widely used than three-dimensional or four-dimensional arrays. But anyway, when you understand the construct, you can generalize this. Okay, so to start with, two-dimensional array conceptually looks like this. Okay, so I will assume that, so these are called rows. So this is row 0, this is row 1, up to a maximum, let's say row r minus 1. Okay, so these are the rows. And row numbering goes like 0, 1, 2, up to r minus 1. So these are essentially row headers. In each row, we have individual elements like this. So these are called columns, and they are independently numbered as 0, 1, 2 up to some c minus 1, where c is the column dimension. Okay. So I would say that a two-dimensional array is conceptually a thing like this. Okay. And we may talk about the, let's say, ijth element. Okay. In a two-dimensional array or in a matrix with R rows and C columns. Okay. So the syntax in C for declaring an array of particular type, which is two-dimensional, is something like this: type. Then you give some name of the array. Then you say maximum number of rows that your array can handle, and this is followed by maximum number of columns that your 2D array can handle. For example, I may have an integer two-dimensional array A with 50 rows and 30 columns. So 0, 1, 2, 3 up to 49, and here 0, 1, 2 up to 29. Okay. So conceptually, it's a 50 by 30 matrix or array or table of int variables. Okay. Okay, so is this construction clear? So you give the type name, maybe int, float, double, and we will today see more complicated things like structures can also appear here. And then give a formal name following these naming conventions, followed by the maximum row dimension, followed by maximum column dimension, both enclosed within a pair of matching square brackets. Okay. So this is the syntax for declaring a two-dimensional array. Okay. So once I have an array like that, A0 refers to the 0th row. I mean the row at index 0. A1, this is the first row. A2, this is the second row, and so on. Until you have, if row dimension is R minus 1, this is the last row. Now each row AI is nothing but each AI. Okay, maybe just delete it. Each AI is a one-dimensional array of whatever type that array element has. Okay. For example, if it is an int, two-dimensional int array, then A0, A1, A2 up to AR minus 1, each of this is an array of int. So if that is the case, the ijth element of A is accessed as the jth element of the ith row. That is, it is AI is the ith row. Now think of this as an array. And if I want to find the jth element, write it this way. Okay. So this is the ith row, and this is the jth element of the ith row, where I and j are essentially indices. They are zero based. Okay.
When she said critic her book. Yeah, so I did this review like completely from this place of like, you know, I have respect for her asking me this. I think we're in a good place. I'm just gonna review it fairly and, you know, as I normally would. And
Okay. So AI is the ith row. The jth element of the ith row is called A within brackets I, then within brackets Aij. So this notation A I comma j is invalid. This cannot be used to access the ijth element. So this is the correct notation. This is the incorrect notation. Okay. So that's about syntax. Not much in it. Maybe we will see. Okay, let us see an example. How to work with two-dimensional arrays. Okay. Maybe this one. Yeah. Okay, so let us look at this and find out what it is doing. Using a macro maxdim, I am defining the maximum dimension to be 4. Then I am working with 3 integer variables I, j, and t, and a two-dimensional array capable of storing 4 rows, maxdim is 4, and 4 columns in each row. So this is how I define my array A, maxdim, maxdim. Okay. Although this is a 4 by 4 array, according to allocation size, I may use some part of it. So I will illustrate what I mean by this. Okay, so maybe I have defined a two-dimensional array. This is C, capital C, sorry. This is capital R, this is the allocation dimension of rows, and this is C. This is the allocation dimension of the number of columns. Okay, but you see that as what happened in the case of 1D arrays, you have declared an array of size S, but you can use inside this array some portion which is of size, let's say, n. So 0 to n minus 1. That because of that you have declared this entire array of size S does not mean that you have to use the entire part of it. So you can actually use some portion of it. For example, maybe this part to this part. So this is 0 to n minus 1. Similarly, in the context of two-dimensional arrays, you can actually use R, some R less than equal to R rows, and you can use some small c less than equal to capital C columns. So in this picture, this is the area that is used for your working part. This is R rows and this is C columns. Okay. Now that you have defined capital R cross capital C matrix, does not mean that you have to use this entire part of it. You can use some smaller part of it, like R, C. Okay. So this is what precisely I am doing in this example here. Although I have defined a 4x4 two-dimensional array, I am actually using 3x3 part of it. So this is 4x4, but I am using only a 3x3 part of it. Okay. So let us see how it works. And I want to put some random values to this 3x3 part located at the top left corner. And then I will make an inline transpose of that matrix. Okay, so that's the simple-minded thing that this code snippet does. Okay, so max dimension 4, you are just declaring a constant. Then you are declaring 3 integer type variables I, j, and t, along with a two-dimensional array capable of storing 4 rows and 4 columns, and they are indexed as 0, 1, 2, 3, 0, 1, 2, 3. Okay. I will use only this part of this array. Okay, this will remain uninitialized. Maybe in a later part of the code execution, I may use this positions, but in this snippet, I am only using this 3x3 part of it. Okay, 0, 1, 2, 0, 1, 2. So for I equal to 0, I less than 3 means 0, 1, 2, j equal to 0, 1, 2. I am simply setting aij to be a random integer in the range 1 to 99. Okay, so let's do it. So this ij, how they evolve, this is shown in this animation. But anyway, conceptually now you are quite comfortable with this kind of double loops. So I am not just going to illustrate further on this. Okay, how ij evolve. Let us see the effect. So 7 comes here, it's 92 comes here, 48 comes here. So that is one iteration of the outer loop, all the iterations of the inner loop. Next, 63, 71, 40. Third row, 35, 95, 39. So that is my initialization to random numbers, random integers in the range 1 to 99 of the 3x3 portion of the array at the top left corner. Okay, I heard certain things. No, not this. Is there a query? No, no. Okay, it's okay. Okay, so these 1, 2, 3, 4, 5, 6, 7 cells are kept or left unutilized for the moment. Maybe later after this code snippet, this is used. Anyway, doesn't matter. Now what I will do, I will make an inline transpose of this matrix. So 7, 71, and 39 will remain where they were, where they are. 63 and 92 will be swapped. 35 and 48 will be swapped, and 95 and 40 will be swapped. So this way I am doing the transpose of a square matrix. Okay, and this loop does precisely that. I'm starting from I equal to 0, 0, 1, 2, and I'm starting from j equal to 0, not j less than 3, but j less than I. So I will run here. This is the row index. Row index runs here. The column index runs here, j. So I will start with 0. J equal to 0, j less than 0. No candidate for j actually in the first iteration. In the second iteration, this will be swapped with this. In the third iteration, this will be swapped with this, and this will be swapped with this. Okay, so let's see how it works. Okay, exiting outer loop. So now I is 0, j is 0, j less than I mean j less than 0. So this condition is not satisfied. So now I becomes 1. So I am at the 1th row, first row at index 1. Then for j equal to 0, j less than 1, so there is only one value of j, that is j is 0. So I will swap aij and aji. So I will store aij 63 in the temporary variable and replace this 63 by 92 and then copy 63 back to this position, 92. Okay, let's see. 63 is copied. Then this 92 will come here. 92 goes here. Then 63 will come here. Okay. And next, so this iteration again ends. The next iteration, I is 2. So j will run from 0 to something less than 2, which is 1. Okay, j is 0. So that means I is 2, j is 0. So I am talking about this 35. So I will swap this with the element A02, which is 48. So 35 will be temporarily stored here. 48 will come here, and then the temporary value will come here. Okay.
Sir,
35.
rand percent 99 means natural number still 99, right?
What?
Rand percent 99 means natural number still 99, right?
Yeah. Rand actually is a stdlib
Yes.
thing.
Inbuilt function.
Inbuilt function. It returns a positive integer, non-negative integer to be more precise. And if I do %99, I get a value between 0 to 98. If I add 1, it will be 1 to 99.
Okay. And sir, basically in this program you are like inputting random values and like just transposing the array, right?
This is just for explaining how you play with two-dimensional array.
Second for loop means you are transposing the array, right?
Yeah, here I am transposing the array in place without using any extra memory. Okay, without using any extra, not memory, without using any extra array. Okay, in place. Okay, so 35 is copied here. Then 48 can come here. And then 35 will come back here. Okay. Then I will have I equal to 2, j equal to 1. So that means I equal to 2, j equal to 1. So 95. This will be swapped with A12, which is 1, 2, 95 and 40. Let us see. 95 is temporarily remembered in T. 40 replaces 95 and then that temporary value comes here. Okay. First loop breaks, second loop also breaks, and we are done. Okay. So this example illustrates several things. One, how to declare an array in two dimensions. Second, how you can individually work with elements Aij. Okay. The third thing that it illustrates is that although this is a 4x4 two-dimensional array that you have declared, you can actually work in something like this 3x3 part or maybe 2x4 part, whatever. Okay. Yeah. So this is fine, right?
Yes, sir.
Yes.
And this actually sets this AIJs randomly. If you want to actually, if you replace that rand thing by scan, so you just can say scanf %d and aij. So if A is an integer array of 2 dimensions, each aij is an integer variable. So as if it is an integer you are reading. Okay. So like and n and I and j, you are reading just and aij. Okay. Okay. So this and thing I will perhaps cover today. Let's see. Okay. So this is it. A little bit. Okay. Anything else here? I don't think so. This is exiting outer loop. So this is done. Okay. So let's forget this. Okay. So then there are a few other topics. Okay. First, how to initialize a 2D array. So this is how you can do it. So there are 2 rows, 3 columns. So it will be like this. 2 rows, 3 columns. Okay. So here it is 0, 1. This is 0, 1, 2. So A00, A01, A02, A10, A11, A12. This way of accessing the elements is called the row measure order of accessing. First row, second row, or 0th row, first row, second row, and so on. And in each row, you mention the elements one after another. Why did you use rand %99 plus 1 and not just rand %100? There is nothing except that I wanted to ensure that the numbers are positive. If you use rand %100, then this will be a random number between 0 and 99. But I ensured a random number between 1 and 99. That's the only reason. That's the only reason. Okay. Incidentally, I can see there is some Anubhav Mandal guest. Who is this? Anyway, let me admit. Okay. 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 So suppose I want to initialize this to 5, 8, minus 2, 4, minus 1, minus 7. Okay. So I can do it this way. So in the row measure order, I can write this 5, 8, minus 2, this is 4. 4, minus 1, minus 7. This is a way of doing it. Although I usually do not do this. There is another way of initializing this. First mention the first row, 5, 8, minus 2. Comma, then 4, minus 1, minus 7. And the third way is we just simply say A00 is 5, A01 is 8, A02 is minus 2, A10 is 4, A11 is minus 1, and A12 is minus 7. Okay. So this is explicit initialization after the declaration, but during declaration you can initialize this way or this way. Okay. And as it happens, but possibly I didn't mention it earlier, if you do not give sufficiently many, I would say, initializing values, whatever remains, they will be initialized to 0. For example, if I simply say 5, 8, minus 2 and then bracket close, then this row 0, 0, 0. Okay. Anyway, don't worry too much about this. This is just a C feature, so may be useful in some contexts. In any case, you always have the option of initializing things this way. Okay. 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 So this is one thing. This is just about some syntax. Second thing, which is more important, is the so-called how is a 2D array stored in your computer's memory. This is actually needed because this will give you an idea how I can pass 2D arrays to functions. Okay. Okay, so now your machine's RAM or whatever, they may be a collection of a two-dimensional collection of cells. They may be even a three-dimensional collection of cells. But the abstract view is that your memory consists of a long sequence of so-called words. Okay, so your RAM, let's say 0, 1, 2, 3, blah, blah, blah. Okay. Now, whenever you declare a 2D array, so this is the conceptual description. The physical description of the RAM depends on the device. It may be a two-dimensional array, it may be a three-dimensional array, it may be a four-dimensional. Okay, how can it be four-dimensional? Anyway, whatever. It may also be a one-dimensional array, but it depends upon what kind of memory you're using. Okay. Now, whenever you declare a 2D array, conceptually, your 2D array, let's say A, will sit somewhere contiguously in A. Now, A is, let's say, row dimension R, C. So, a total of a memory capable of storing a total of the basic data type with RC elements. So, this is how this A is stored. Okay. So, RC cells for A. And if it is an int, that means 4 RC bytes. If it is double, this means 8 RC bytes, and so on. If it is a character, it's just RC bytes. Okay. So this is what is called a contiguous representation. Okay. So there is a total of RC cells here of the data type that A has. Let's say int. So there are RC ints. Okay. So this is the abstract view. You do not know how your RAM or your memory device is actually organized in the I would say in the silicon chip or whatever, but we typically view it as a flattened thing, and a two-dimensional R by C array is also viewed as a contiguous one-dimensional representation, flattened. Okay. So it is important to understand how this is organized. Okay. So I have A00. Yeah, tell.
Sir, I am Anubhav Mondal, and I think the Anubhav Mondal you just now accepted into the team is someone from outside who doesn't belong to IIT KGP.
Is it so?
Yes, sir. I am the real one. Just now someone tried to enter using my name
Okay, I will find
with
out.
the wrong spelling and no roll number and no department and no email ID.
Okay, okay, okay. I will figure out. Let him stay for the
Yes.
moment. Next time.
Okay, sir. Thank you, sir.
Okay, so okay, so let's see. So this is 0, 1, 2 up to r minus 1, which is 0, 1, 2 up to c minus 1. So I have an element here, an element here, an element here, and so on. Then I have an element here, element here, element here, and so on. Likewise here, 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 here. So what the contiguous representation stores is first this element, then 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 this element. So it's something like A00, A01, and so on. Then we have A0C minus 1. And let's say this is followed by A10. Okay. So the flattened representation is the row measure representation of the 2D array. To be more precise, if I have a more concrete example, let's see. If I have a 3 by 2 array, so this is 3, this is 2, and let us have 7 minus 2, 3, 9, 4, 8, 4. Then in the contiguous representation, it will be stored as 7 minus 2, 3, 9, 8, 4. Okay, starting at some point, ending at some point. 7 minus 2, 3, 9, 8, 4. Okay. So this is the conceptual array, and this is its organization in the memory. Okay.
Excuse me, sir.
Yeah, tell.
For such two-dimensional character array,
Two-dimensional character array, yeah.
how many non-terminating character we will use for each row?
Each row you can null terminate, yes. I mentioned this, right? A0 is the 0th row, which is itself a one-dimensional array of type. So if your type is character, A0 is a character array. A1 is a character array. A2 is a character array. So you can use A0, A1, A2 individually as null-terminated strings. No problem. Okay. Oops.
So, at one particular time, like in which major form does the computer decide to store the double-dimensional array?
At what
So
is it?
suppose I create two double-dimensional arrays.
Okay.
Then will both these double-dimensional arrays be stored in the same major form? Like if the first one is stored
Yes,
in row
yes.
method form.
Yes, yes. At different places in the memory.
Yes, sir. Then, like, how does the computer decide, like, in which major form to?
That is what I am going to explain now. It actually suffices to store only this address. Okay, so this is essentially the address of this element. Okay, so now let us see. If they are C columns, then if I have an ijth element, so this is my 2D and this is my flattened representation. So if I comma j is the logical row and column number of an element in the 2D array, what will be the index of the same element in the flattened representation? You see that you have to skip I rows. Each row has C elements. So you have to skip IC cells in the flattened representation in order to skip whatever comes before row C, and then you have to go to the jth element. Okay, so if the column dimension is C, this is C, this is R, then the logical or conceptual two-dimensional coordinates I, j maps to IC plus j in this flattened representation. Agree or not?
Sir, I did not understand the IC plus J part. Can you explain once again?
Here, for example, this 9 is at location. Okay, let me give the indices 0, 1, 2, 0, 1. So 9 is at location 0, 2, right? Sorry, 1, 2. No, 1, 1.
1.
1, 1. So 9 here at conceptually at position 1, 1. And what will be the position here with respect to this flattened representation? Column dimension is 2, so it will be 1 times 2 plus 1, which is 3. And you can see that 0, 1, 2, 3. This is where 9 resides. So this map from row number I, column number j to the index in the flattened representation is this formula. I, j goes to IC plus j, where C is the column dimension of the two-dimensional array. Is this clear now?
Yes, sir.
Okay.
Yes, sir.
Okay. Conversely, so this goes to this. Conversely, if I have an element at some index k in the flattened representation, what will be its two-dimensional coordinates? So here actually I is between 0 to R minus 1 and j is between 0 to C minus 1. So you can simply work out this is j will be k percent C and I will be k by C. So these are integer divisions. So this is quotient, this is remainder. Happy or not? So I, j will go to IC plus j. On the other hand, if I start from some index k in this flattened representation, the corresponding I, j in this two-dimensional conceptual representation is k by c, integer division. This is basically floor and k percent c. Agree or not?
So what if J is also like? Oh no, it will always be smaller. Okay, got it.
Okay. In particular, whenever you say Aij, this address A is remembered along with the column dimension C. So the machine will use this formula IC plus J. Starting from A, it will go to the whatever this quantity is, it will skip this many cells and go there. And that is how Aij will be located in the flattened memory. Okay. The converse, I would say, transformation is not perhaps needed by the compiler because you are accessing as Aij. Okay, not in the flattened form. But anyway, it's good to know the formulas in both the directions. Okay. So now look at these formulas and realize that these index computations, they require C but not R. With the only restriction that I should be restricted from 0 to R minus 1, J should be restricted to 0 to C minus 1. Other than that, these formulas do not involve the row dimension. They only work with the column dimension. Agree or not?
Yes, sir.
Okay. Yeah. Now, if you supply a value of I greater than R or greater than equal to R, it's your headache. You have overshoot the memory. Likewise, if you give a value of J bigger than C or greater than equal to C, it's your problem. It's not C compiler's problem. C compiler will simply use this formula IC plus J and go to that location. Okay. If that means you are accessing somewhere which is beyond your intention, it may go outside this. Or if you say just 2 or 1, 0, 1, 1, 2, then it will be 1, 2 plus 2, 4. Location 4, 0, 1, 2, 3, 4. You will actually access 8 instead of somewhere here. Okay. So it's your duty to ensure that I and J are in the correct range, respective correct ranges. Okay. Then only the intended element will be accessed. The computer will use this formula and go there and try to retrieve it. If it is outside your memory, you may encounter segmentation fault and many other things may happen. So it is your duty to ensure the sanctity of I and J values. It is exactly the same as in the case of one-dimensional arrays. There is no range checking. But what is important in this context is to know that the compiler must know this capital C. Without that, it cannot convert your logical I, J coordinates to the index in the flattened representation. Row dimension is not needed. Okay. This understanding helps us understand what follows now. Passing 2D arrays to functions.
Excuse me, sir.
Yeah.
Sir, here that C is how many are filled or how much we had initially given max dimension.
C is the allocation dimension.
Okay, sir.
Not exactly what you are using. Okay. So that's important to know. So if this is your allocation dimension and you are actually using this part, then the compiler will essentially, this part will be followed by this part. So this part and this part are not contiguous. This will be followed by this part, some unused part. This is followed by this. This is followed by again some unused part and so on. So if you actually want to correctly locate an element I, J in your working part, you should tell the computer, the compiler, what this allocation dimension is, not what this is. Needed? This is needed, right?
Yes, sir.
Okay. because a small r by small c part has different contiguous representation than a capital R by capital C part or 2D array. Okay, so that's it. So this C is the allocation dimension. Okay, not the actual dimension that you are using. Good. Okay, so you think about what you have done for 1D arrays. So you passed, let's say, an int array A and maybe int n. You could also pass this at A25, A max dim, doesn't matter. To the C compiler, only this much is sufficient to know that it's a one-dimensional array that it is dealing with. What its allocation size 25 or max dim or whatever, that is not relevant. Yes or no? This is what we have done, right? Although if you specify something like 25 max dim or something like that, this doesn't hurt. The compiler will simply ignore whatever is there. Okay. So this, if there is anything, this will be ignored. Yes or no?
Yes, sir.
Okay.
Yes, sir.
Now for a 2D array, I have two dimensions, R and C. Just now we have seen that the compiler needs to know this capital C, otherwise it cannot convert I, j to a coordinate or to an index in the flattened representation. Okay. Therefore, you have to pass this capital C. This is mandatory. Otherwise, the C compiler cannot make index calculations. But as we have seen here, R does not play any role in these calculations here or backward calculation here. Therefore, this is optional. Or for that matter, if present, it's simply ignored like this. Okay. So you
Excuse me,
have to specify the column dimension, but you can simply keep the row dimension. If you can put anything there, but it will be simply ignored. So in other words,
So, so the only the C is supposed to be mandatory in this case, right?
yes. Yeah,
But in
yeah.
code blocks, they generate an error and say that in multidimensional arrays, all bounds have to be specified. Like if I only specify the second one.
You have to specify the second one. First one is not necessary. If you give something there, the compiler will not complain, but it will simply ignore it.
Yes,
No
sir,
complaint. But if
the
you do not
compiler.
specify this, the compiler, your code will not compile.
So, but in code blocks, it raises this error saying, or in multidimensional arrays, all bounds have to be specified.
That is not what my understanding was. Anyway, let me write down. So whatever void or int or whatever the function returns, f, then int, let's say an int array. This is not needed, but this column dimension must be specified. You can have some row dimension here, it will be ignored as I mentioned. If you write a row dim, column dim, there is no harm. And then if you want to actually use something like an R by C part of this two-dimensional array, you like this, like, yeah, here. In addition to this, you specified this n, which is the used portion of this array. Here also, if you want to use this used portion is R cross C, which is smaller than row dim and column dim. You may additionally pass this RC. Okay. And like 1D arrays, array elements are, I would say, visible from inside the function. Okay. So if you say a to 5 equal to 19, okay, maybe in main you have an array int b 30 30. Okay, then you should somewhere define column dim as 30. Then you may call f b or c maybe 10 by 15. Okay, so no brackets and nothing here, you just give the name in the call. But this one and this one must match. If they do not match, then you may actually find funny results, even segmentation faults and things like that. Okay, you can write things here, row dimension here, 30 here, 100 here. Even if that is not the actual allocation dimension. This does not hurt, but you can also keep it just empty. This is mandatory and this must match this. Otherwise, your code will have severe bugs and may even encounter segmentation faults. Yes or no?
Sir, while calling the function from main, we just have to pass the array name. We don't have to mention any dimension.
It is already known to have dimension 30 by 30. Now the name suffices.
Okay, sir.
Right.
Sir, so a given function only works for a certain column dimension for an array.
Yes. If you want to work with arbitrary arrays of any row dimension, any column dimension, then you have to do something separate, and we will come to that possibly in the next week or maybe next to next week. Yes, you are correct. This will work only with matrices or two-dimensional arrays whose column dimension is column dim. 30, 30. If you have another thing like int c 50, 50, you cannot pass it to this. True. You are absolutely correct. Yes. Okay, so that's it. That's all I wanted to tell about two-dimensional arrays. When we study pointers, we will once again revisit the notions of two-dimensional arrays.
Sir?
Yeah.
Sir, can we edit the element inside this inside that function by this input?
AIJ, you mean?
Yes, sir. In the AIJ 2D array, can we change the elements that are present inside this function using this type of input only?
This type of input, I do not know what you mean by. You can say A00 or A03.
Somewhere we use pointers to change the things that are inside, to change the things in the main.
No, let's see. If I say A03 equal to 5 here, this B03 will change. That's why I said array elements are visible from inside the function. So if you say this will change.
Okay, sir. Yes, sir.
This is exactly the same as in the case of one-dimensional arrays. Exactly the same. Because A is nothing but a pointer. But what kind of pointer? This we will see later. A complicated thing. This A, this B, these are nothing but pointers. Okay. So but for 2D arrays, the pointer is little bit complicated. So anyway, I will come to that when time comes. But I believe this is all you need to know as a working knowledge of using 2D arrays. Okay, so what's the time? 4:11. Maybe let us have a 5 minutes break. Then I will start structures. Okay. So hello, I am back. Okay, so yeah, we will come back again to two-dimensional arrays when we talk about pointers, but that treatise will be a little bit complicated anyway. Let's move on.
Yes, sir.
Oh, yeah.
Regarding the last thing that you just said,
What is
that when we will return to 2D when we start pointers, that is.
Oh, no.
Sir, so I tried to write a function using 2D array as a parameter. It is not taking, like if I declare, for example, function f with a function parameter of 2D array, it is not working.
I am not sure. This kind of thing.
Sir, I have tried it out again, but in my case it is working. Like I am only specifying the column dimension, it is working.
No, it
In
should
my
work.
case.
That is the
Well,
specification.
sir, in that case, column dimension has to be declared global.
Yeah, that's why I have defined column dimension. But you just write 30 here, no problem.
Then it will work. Otherwise, like for example, if we are like, for example, opening bracket, close bracket, open bracket, close bracket, then it will.
No,
work.
that will not work. Okay, this will not work. This will not work. This
Sir?
will,
Yes, not working.
this will not. This will also not work. If you say R row dimension this will also not work. But if you say int ARC, this will work because this R will be simply ignored. This is fine. This must be present. Yeah, there is another question. Tell.
Sir, what is int R and int C?
What?
Sir, int R, int C.
This RC, this is row dimension, column dimension, something like that. Okay.
So, sir, these are row size and column size.
Yeah. This is R, this is C. Okay. I do not have enough space to write row dim here. That's why I am writing just R.
No, sir, small r, small c.
Oh, smaller and small c is something that is illustrated by some picture. Yeah. Here, this is my C. This is my R. But actually, I want to use only small r rows and small c columns. Okay.
Sir, one question, sir. Does this then means that the compiler by default uses row major technique only, and not the column major one?
No, yeah. This is
Stored.
the default. This is the C specification.
Okay, sir.
Yeah. You cannot change it to any other representation. Okay. 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 So now let us look at this. An array, whether it is one-dimensional or two-dimensional, is what can be called a homogeneous collection. So it can be a 1D array or a 2D array of integers or characters or things like that. What if I want to do work with heterogeneous collections? Let us think of this. Okay. Let us think of this, a student.
Hello. Sir, can you say about homogeneous collection? What does it mean?
Every element that collection is of the same data type. It's an integer array or character array, one dimension or two dimension, whatever it is. And what I mean by heterogeneous.
Type of which rows or columns? same data type of use both rows or columns?
Each element. Whether it's a two-dimensional array or one-dimensional array, it doesn't matter. Each element is either int or char or something like that. Okay. So this is what is meant by homogeneous. Yeah. Okay. So now suppose you want to store against a student several things. Maybe a name. Maybe a roll number. CGPA. Age. Okay. So this is basically, let's say, a character array. So char name 100. Roll number is also a character array. In IIT KGP at least. It's usually how many digits, how many characters? So that's 9. So maybe 10 characters suffice. CGPA is a floating point thing. Maybe float or double. Float is sufficient. Age may be just integer or unsigned integer. So I want to club together all this. Sorry, this is not name. Maybe roll or roll number, whatever. Now an array cannot store different types of things. Characters, character arrays, floating point things, integers, and all that stuff. Okay. But it would be good if I have these types of things and many other things perhaps encapsulated in the form of a single, in a sense, object. Okay. So if I want to, so this is what I mean by this. This is a character array. This is another character array. This is a float. This is an int. So these are heterogeneous types of things. So they can all be included or encapsulated in a structured data type. Okay. So the motivation is clear, right? An array is as such incapable of storing different types of data, character arrays, floats, integers, other things also, pointers, two-dimensional arrays. Okay. So an array is not exactly meant for doing it. So if I want to encapsulate things of different types, I may use what is called a structure. Okay. So typically a structure is defined this way. This is the C syntax. Struct. Give it a tag for the moment. Okay. Type 1, member 1. Type 2, member 2. And so on. So from type K, member K. Okay. So these individual types may be different. and the formal names are member 1, member 2 up to member k. For example, I can define the student structure this way: struct stud. First one is a character array, name 100, character roll number or roll 10, float CGPA, int h. Then bracket close, and don't forget this semicolon. Okay. So this now gives a heterogeneous collection like this. Name is a character array of size 100, roll number or roll is a character array of size 10, CGPA is a floating point variable, and age is a int variable. Okay. This way you can define your heterogeneous collection. Struct, give a tag. This tag is actually not necessary if you do something. I will come to that a little later. Then this defines a new data type called struct stud. Okay. So later, instead of int or float, I can use struct stud. Let us see a name. Maybe, yeah. So it is a single structure of this. You can have, PDS 1000 and so on. So this gives you a single instance of a heterogeneous collection like this, whereas this gives an array of collections of 100 things like this. Okay. So just think of this as if you are using int or float. Float, Krish means Krish is a floating point variable. Whereas float PDS 1000 means it's a floating point array with 100 or 1000 elements. Okay. Now this struct stud, by this declaration, you have declared a heterogeneous collection, the name of it, struct stud, and then you can individually declare variables or arrays of this type. Okay. Then this is about declaration. Next question is, how do you initialize? Sorry, initializing will come a little later. Maybe it's not so important. How do you access the individual members? Krish has a name, Krish has a roll number, Krish has a CGPA, Krish has an age, right? And their data types are character array with 100 elements, character array with 10 elements, floating point variable, and an int variable, respectively. Likewise, I have PDS 0, PDS 1 up to PDS 999. Each one of these will have these things. PDS I will have a name, PDS I will have a roll number, a CGPA, and an age, and their types are character array, float, and int. Okay. So these individual elements can be accessed this way. For example, for Krish, I can simply say, okay, let me do this way. Okay. I can do it this way. For example, strcpy Krish dot name. So this is the thing. Use a dot followed by whatever the member name you have given. Let me go there again. The member names are name, role, CGPA, and age. So Krish dot name will refer to this character array. Krish dot role will refer to this character array. Krish dot CGPA will refer to this floating point variable. Okay. So I can use them. Some things like this. Okay. Krish.name is nothing but a character array capable of storing 100 characters. So I can copy this string to this. Okay. Likewise, I can say.
Sir,
Yeah.
why can't we directly write Krish.name is equal to within the double quotes EV Krishnamurthy, like we normally do?
No, we don't normally do that. If I have a
It
character
would
array,
not work.
S10.
I did the same in the assignment, then realized that it does not work.
Yeah. Can you say S equal to I am Krish? You cannot do it, right? So Krish.name is just a character array. Whatever you can do with your character array, you can do it here. This is not allowed. But you can initialize it this way.
Okay, sir, I confused there.
Okay. This is allowed. This
Yes,
is not
got it.
okay.
Sir,
so
and here Krish is not the name. Krish is the Krish has replaced student.
Krish is a
Start.
struct stud.
Okay, sir.
Okay.
Yes.
Like int, it is now a composite data structure, data type, consisting of one name, one roll number, one CGPA, and one age. So I am explaining this. Krish dot roll maybe 20 FB 5. And
Hello.
CGPA. Yeah.
Sir, what is Krish here? Krish is the
It's a variable. If instead of int, I say int I becomes an int type variable. Now by
okay.
this is a variable. And this is an array of 1,000 structures of type struct stud. Okay. CGPA equal to, maybe you can calculate from database, give some database name, blah, 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 whatever.
Sir, could you repeat what PDS was?
Yeah, I will come to that. Chris dot, what is that? Edge. Maybe 20. Okay. This is fine.
I had a doubt, sir, here. In string copy, if we have a space in this string constant, then will it get copied?
Yeah, string copy will work.
Okay.
Non-terminated strings. Okay. Only scanf will not work. Scanf will read only E. Break at this space. String copy has no problem. Okay. Then instead of Krish, I can do it for these things. Whatever I have done here, if I replace this Krish by PDS0, PDS1 or PDSI for that matter, all these things will work. Okay, because this capital PDS is nothing but an array of 1000 structures of type struct stud. Okay, so PDS 0 will essentially refer to a structure at index 0. PDS 1 will refer to this structure at index 1 and so on. So since that is a structure, if I say dot name, it will refer to that character array. Okay, so it looks like this. Let's see how it looks like.
Excuse me, sir.
Yeah.
So here, how do we know index of which variable is which?
There are many things I have not yet covered. One by one, I will do things. Okay. 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 So that PDS array will look like this. This is a structure. This is another structure. This is another structure. This is another structure, and so on. So this is PDS 0. This will have those 4 things. This is PDS 1. This will have those 4 things. PDS 2, and so on. Okay. So definitely the question is, how do I calculate the index of PDS1? You do not have to worry too much about it for the moment, because the compiler knows that this is an array of that kind of structure. Okay. So it will do the inherent calculations, whatever is needed, in order to access PDS0, PDS1, PDS2, PDSi for that matter. And then if you say dot name, dot role, dot CGPA, dot age, it will individually refer to these variables. Okay. Yes or no? You don't have to really worry about how these things are organized in the memory. Okay. Simply say PDS0. If you say PDS1, the compiler will actually skip these many things and go to access this record. And what is the amount of skip that the compiler does? You can also do it. It is the size of struct stud. Whatever it, 120 bytes, 150 bytes, whatever is needed. Maybe something like 100 plus 10, 110 for 114. This is also for 118, but you most likely will see 120. Okay. Typically, these things are allocated at a chunk of, 4 or something like that. But anyway, this actual size that the compiler will skip for accessing the second record or the third record or the fourth or for that matter the ith record, this is governed by this quantity, size of struct stud. So size of is actually something. You can also say size of crash or anything, size of PDS0, sorry. Okay, it need not be only a data type. You can give some variable names. Okay, so the size of thing I suggest that you study. Maybe I will, if time permits today, I will just give you an introduction. I will just write a short code. Okay. So this is a homogeneous collection of heterogeneous collections. This is what PDS is, right? Each of these PDS0, PDS1, PDS2 is a structure, whereas overall PDS is an array of these structures. Happy or no?
Yes, sir.
And the amount of skip can be obtained by using this size of struct or size of any variable of that type, Krish or PDS0 or whatever. Okay. Okay, so the size of is not a macro, but anyway, what it is you don't have to remember or you don't have to worry about right now. Okay, so that's how you declare, and what else? There is Okay, so I told that tag is not necessary. So in C, there is something called type definition. And then you have those things, char, name 100, char, roll 10, float, CGPA, int, edge. Then you give a name here. So type def is often useful in C. That this is nothing but a C syntax. The point is that this tag is necessary here. Okay, here. Why? Because in the next declaration you can have struct teacher. Then teachers also have character names, but not roll numbers usually. But maybe here we have EC numbers. We do not have CGPA, but of course we have ages. So then there are several other things that may be in the struct. So if you just say struct, the compiler does not know whether it is a struct student or struct teacher, right? So you have to give the, I would say, a tag. Otherwise, struct is just a keyword. If you just say struct Krish, what kind of structure is it? You do not know. Okay, the compiler doesn't know. It may be struct stud, struct teacher, struct department, many things. But if you define the type of the structure with this new name, then this is not necessary. Because you have given the new name student to a structure of this type. Later, instead of struct stud, you can use student this way. Okay, if you had stud here, you can also write it in the earlier way, struct stud k, maybe another course, math 1, things like this. But if you give a formal name using this type definition, then later instead of struct whatever this tag, you can use this. And if you have a type definition, then actually this tag is not necessary because you can refer to this as student. Yes or no? But a single struct will not do. Okay, you cannot say struct k. What kind of structure it is? The compiler must know. Okay. Happy or not?
Yes, sir.
Okay. So the operator is dot for accessing individual elements, and you have this arrays and all that stuff. Okay. I was thinking of telling you something. Okay, type def. Yeah. Type def is just a command which gives a new name to a type. So if you are very much tired of writing unsigned long int x, you can also do this thing, type def unsigned long int, but now you have to give some name, maybe ULLI. Later, instead of doing this, you can simply say ULLIX. So type def has nothing to do with, I would say, structures only. If you have an already defined data type, you can give it a new name. So typedef essentially gives a new name. To a data type, which is already defined. Okay. Or in the course of definition. Here I am defining this, and alongside this definition, I am giving it a new name called student. So instead of struct stud, I can use student. Okay. So if I use a struct definition in conjunction with a type def, this is for the moment not necessary, but there is an exception. I will come to that when we talk about pointers. Okay. Okay, so that's all about syntaxes. Maybe I give you just a last an example. Okay. So if you have struct stud A, comma B, this is allowed. Okay, so what will happen? So A has the size of struct stud bytes here. B has struct stud size of struct stud bytes here. So this will make a byte by byte copy of B to A. So it will create an exact replica. So if there are character arrays, they will be verbatim copied inside a structure. But, so this is allowed. Assignment of one struct to a struct of the same kind is allowed. But what is not allowed is a thing like A equal to B plus C. If you have two structures, three structures, A, B, and C, this is not allowed. Okay. That does not make enough sense because you do not know what is the rule of addition. Okay, not allowed in C. Okay, in C, of course, we are doing C only. This kind of things are allowed in C++ after what is called operator overloading, but anyway, you don't need to worry about that. So whenever you say a structure equal to the structure of the same kind, whatever the total amount of storage needed for the structure B, okay, so this everything will be byte by byte copied to this structure. Okay, so this is one important thing. In fact, you can let the functions return structure variables. So I will demonstrate this using an example. This is no longer a, I would say, a student type of structure, which is heterogeneous. But anyway, this will illustrate things.
Sir, I had a doubt.
Yeah.
Sir, in the assignment of one structure to other, suppose we have two structures having similar type of data, means similar data types declared inside.
Not allowed.
Not allowed. Okay,
Not
okay, sir.
Yeah. Even if their size of gives the same thing, this is not allowed. This
Means
will
they should be of the same, under the same structure only, means.
Exactly.
Okay, okay.
In fact, if you have something like this, struct stud equal to this name, roles, GPA, and then you define struct stud 1, same thing, cal name 100, cal roll 110, this will also not be allowed. Okay, they must be of the same type, exactly the same type. And what will happen if you do some kind of typecasting? I have to experiment. I do not know exactly what will happen. Okay, typecasting, explicit typecasting. Yeah, we have to work out. I do not know.
Okay, sir. Thank you.
Okay, so here what I have done, this is, I am defining its structure, although this is a complex variable with integer real and imaginary part. Okay, so int real, int imaginary, and since this is actually a homogeneous collection because both the elements are integers, I can also declare this as this kind of things also, but too many things in the syntax. Type def int complex 2. This also works, but anyway, this is getting too much of the syntax. Let's not worry too much about it. This way also you can declare a complex to be an array of size 2 integers. Okay, anyway, but here what I have done, so this is allowed. But anyway, here what I have done, I have actually made a homogeneous collection in a heterogeneous format, having two parts, real and imaginary, and I'm calling that structure as complex. I am not using any tag here because I can anyway access variables of the structure type as complex. Okay, and let's see what happens inside the main function. Okay, so I declared 3 variables A, B, and C of this type. Okay, then I set the real part of A as 1 and imaginary part of 2, imaginary part of A as 2. Then I simply assign B equal to A. So that means this real part will be copied to the real part of B. The imaginary part of A will be copied to the imaginary part of B. Okay. Then I can pass this A and B as parameters. So here I can have complex A, complex B, or if you have something, some tags, struct comp, I could have passed struct comp A, struct comp B, and so on. It is also going to return this the complex product of A and B, and whatever it returns, it will be stored in this data type C. Okay, and the code is fairly straightforward. Create a local complex variable C. Its real part will be A real times B real minus A imaginary times B imaginary, and the imaginary part will be real imaginary, imaginary real. Okay, so you populate the real and imaginary parts of this C and simply return it. And whatever is returned, this will be stored in C. Okay, so passing structures, returning structures is fairly straightforward. You only need to define and access individual elements. Here I am accessing individual elements like this .re.im. Here I am accessing like the same way .re.im and so on. And copy of structures of one type to a structure of the same type can be done as it is illustrated here. Okay, so let me show the visualization of this. Yeah.
Sir, I had a doubt. If we define the structure inside main, then this code will throw an error, no? Because then the function does not have any information about the structure.
Yeah.
So here also in structure definition also we have global and local types.
Yeah, this is global, right? Not inside main.
Okay, sir.
And I didn't try, but I don't know whether you can define structures inside functions. Maybe this is allowed, maybe this is not allowed. I am not very much sure. I typically do not use this kind of programming. Okay, but you may try. If I define this inside this, whether the compiler accepts it or not, but then the definition of the structure or the use of the structure is restricted to that function only. It is not accessible from outside. That is true. Even if it is allowed, then if it is not in a global scope, you can use that only inside that scope or subscopes. Okay, so let us see how it works. Okay.
So,
yeah, tell.
So I had a doubt in the struct start example. When we made the assignment A equal to B, will any change in A dot name be reflected in B dot name?
Yeah, everything will be copied. Oh, no.
For the array, I am talking.
No. A equal to B means everything, whatever is sitting in B will be copied to A. They are still two different copies. But then if you change A, B will be unaffected. If you change B, A will be unaffected. Okay. Yeah, something like that.
Sir,
Yeah. Now doubt is clear. Yeah.
sir, how come we are allowed to return a structure as in a function, but we're not allowed to return an array?
What? No. What?
So here we are returning when we say return C in the function cmul.
Yeah.
Then are we returning a structure?
All those bytes that is given is returned, but size of this entire thing will be returned. This is not a pointer. A structure is not a pointer. A structure essentially means that entire thing, whatever is sitting inside this compound object, that entire thing will be returned byte by byte. And they will be used to assign all the relevant bytes of C. So a structure is not a pointer. Keep it in mind. An array is a pointer. A structure is not a pointer. The structure may contain pointers, may contain arrays, but whatever it is itself not a pointer. Is that clear?
Yes, sir.
Okay, so main, let's see. So here you declare three things, A, B, and C. So this is, I think, the real part. This is the imaginary part. So there is a memory for main. A, B, and C, three things are declared like this. Then you say A real equal to 1. So this will get 1. Then you say A imaginary equal to 2. So this will get 2. Then you simply say B equal to A. So entire thing contained in A will be copied to B. Okay. So B equal to A, copying A to B. So the entire thing will come here. So this will also become 1, 2. Okay. Then you are passing to this CMUL function A and B. But once again, note that these are not pointers. These are like int variables. So whenever you call a function, a copy of A will go to the function with the name A. Likewise, a copy of this B will go to this B. Okay. So let me again iterate. A structure is not a pointer. So what will happen? Main calling CMUL. So CMUL's memory will have a copy of this A with the same name A. Of course, I could have used C and D here, and then this will be C, this will be D. But anyway, this A and this A, they are not the same. This A is a copy of this A and this B is a copy of this B. This means that if I make any change to this is not visible to this A. Likewise, if I make any change to this B, this will not be reflected here. Okay, so this is not an array. So first A and B are copied to this A and B. Then you have complex C. So this is a local variable. So there is a space for this local variable. C, again, this C has nothing to do with this. but this C will be returned and will be used to populate this C. This C. Okay. So you compute 1 star 1 minus 2 star 2. This is this. This real part will be minus 3. This will be 1 times 2, 1 times 2, 4. 4 will come here with the local calculations. Then you are returning C. Okay. And that return value will be used to populate this C. So minus 3 will be copied here, minus 4 will be copied here. Okay. And after this function returns, okay, so there is some minus 3, 4 floating somewhere. This will be used to populate this. Okay. Return value is copied to mains memory. That's done. Okay. Okay. Back. So note that after this returns, like all local variables or parameters, this A, this B, this C, these are just gone. You can no longer refer to them. Okay. But the return value, of course, this parenthesis is not necessary. You can just say return space C. This will be used to give values to the real and imaginary part of this C, and that's it. Yeah, so that's about structures. Maybe a few other small things I forgot to mention, but more or less it's this. Yeah. So maybe I stop here today. So if you have doubts, let me know.
Sir?
Yeah.
Sir, can we pass reference variables into a function in C?
What is that? What do you mean by that?
So like in C++, we can pass a reference to a local variable in the main into a function, so
Like
that we can directly change it. I mean, pass by reference. What?
Yeah, int and A.
Yes, sir. Int and A, int and B.
This is not allowed in C.
Okay, sir.
This is only a C++ feature.
Sir, so if we, for example, in C++, if I can write a struct inside the main function, then if I pass it by reference into a function, then will it work directly? I mean, without creating a copy.
No. I mean, defining structures locally in C or C++, what will happen, I exactly do not know. I have to experiment.
Okay, sir.
Okay. Because even in the case of C, what will happen, I do not know. Whether it is, whether the compiler will allow me to do it, that is also not clear. I have to write it.
Okay, sir. I will check.
We have to check. This is a tricky question. Anyway. Yeah, so that's it. Maybe I will next day start a little bit with the remaining things about structures, if any. If any important is left today, otherwise next week we will start pointers. Yeah, you tell if you have any further doubts on today's coverage.
Sir, when marks will be released?
Huh?
Marks, sir.
Which marks?
Test, when it will be released?
No, I don't understand your question.
Sir, when will marks of our test be released?
Marks for which test?
It's a long test one.
Sir,
Mid-semester examination. Yeah, let us finish the grading. So we will take at least this week. So 1,000 students, 900 plus students, it's difficult. We will try to do it in this week. That's it. That's in our plan. Maybe next week sometime we hope that all of us will have time to complete our own parts. And once we are done, we will let you know. And we are also thinking something about the shortest one. You may go and check in Moodle. You may see your marks. Whether or not we will do anything with it, we will see later. In fact, we are thinking of one thing. We will take another short test 2 that will not be in the next week, next week, because we do not have enough time. And I hope there will be no problem in that, because we will run that short test 2 in the same configuration, or almost same configuration like mid-sem. So network delays should not be an issue. And yeah.
Sir, the review of short test 1 is not permitted in Moodle.
Not yet permitted. Okay.
No,
Then,
sir.
then maybe some problem. So my co-teacher is overlooking, looking at it. So we will do it soon. That's what we concluded. So maybe some evaluations are still missing. Maybe after that we will open it. And maybe in the end we can take the better of short test 1, short test 2. Because although this short test 1 was a bad experience for many of you, but it is also possible that a few of you actually were, did pretty well there. So maybe just completely ignoring it is not a good idea, perhaps. Anyway, we will see. But next week, possibly during the class time, most likely on Tuesday, class time or the hour after the class time, we will take a second short test. Syllabus will be more or less whatever we can complete in this week and next week. Yeah. Yeah. So yeah. Any other questions related to tests, today's coverage, and other things?
Sir.
Yeah.
Sir, in the last code, like there are in C there are values like -3 and 4. So to print them, like we have to use like C.real and C.image in printf, or either we can print them normally by using C.
Your question is not clear. Look, if I look at this, if I have a struct Kris.CGPA is a float. Whatever you can do with a float variable, you can do it with Kris.CGPA. Whatever you can do with an int variable, you can do with PDS13.h. You can scan, you can print, you can use it in other expressions, assign values to that. Whatever you can do with int, you can do. Only thing, you have to access that thing by PDS some index.h. It becomes an int variable. Whatever you do with whatever you are allowed to do with an int variable, you can do on that. Does that answer your question?
Yes, sir. Thank you, sir.
Yeah.
So basically by using structures, we are defining our own data types, right? And then we can, and the members are the, those members of the data type.
Yes, yes. This is a composite data types, you can say.
Okay, sir.
Yeah. Oh, there is a question. If there is a 3-dimensional, yeah, you can have 3-dimensional, 4-dimensional, whatever. Only thing you have to define, yeah. Where did I define? Yeah, like this. So int A, 2, 3, 4. Another dimension you add. 4th dimension, 2, 3, 4, 3. Okay. But let's not worry too much about more than 2 dimensions. Yeah. Multiple dimensions are allowed, yeah. Beyond 2, it's allowed in C. It's good to know that, but let's not worry too much about 3-dimensional arrays. Yeah. Anything else? Yeah, then I think 2 constants are needed. Yes, 2 constants are needed, definitely. Yeah, but let's not worry too much about this. Yeah, so if you have no questions, let us call it a day.
Thank you, sir.
Okay.
Thank you, sir.
Thank you. Let me stop my presentation. Okay.
Thank you, sir.